Okay, so the last part of this chapter is solving exponential equations. So we're going to determine the solution of an exponential equation in which the bases are powers of one another. We'll solve some problems involving exponential growth or decay, and also problems that involve the application of exponential equations to loans, mortgages, and investments. So an exponential equation is an equation that has a variable in the exponent. So we're going to see that we can solve, excuse me, we can solve some of these algebraically by making the bases the same. So we'll look at that today. How do we solve exponential equations where we can make the bases the same? If we can't make the bases the same, then that's one of the applications of logarithms, which will be chapter 8. Okay, so it says exponential expressions can be written in different ways. It is often useful to rewrite an exponential expression using a different base than the one that is given. This is helpful when solving exponential equations because the exponents of an exponential expression with the same base can be equated to each other. For example, if you have this equation, 4 to the 2x equals 8 to the x plus 1. Those are exponential equations because the variable is in the exponent. And you can rewrite those with the same base because both 4 and 8 can be written with a base of 2 as a power of 2. 4 is 2 squared, and that's raised to the 2x. 8 is 2 cubed, that is then raised to the x plus 1. And then you're going to get 2 to the 4x equaling 2 to the 3x plus 3 when you multiply those exponents. Now, this equal sign tells us that the two sides are equal. If one part of them are equal, then the other parts are equal as well. Meaning, if the bases are equal, then the exponents will be equal as well. And so that's what we can say. Because they both have a base of 2 and the bases are equal, then the other parts, the exponents, are equal as well. So the exponent 4x equals the exponent 3x plus 3, and then you can solve for x. So this method of solving an equation, exponential equation, is based on the property that if c to the x equals c to the y, then x must equal y, as long as c doesn't equal -1, 0, or 1. And so that's the process that we're going to use. But first, just to get some practice working with changing the base, this first question says rewrite each expression as a power with a base of 3. Well, 27, that is 3 to the power 3. 9 squared, you'd write the 9 with a base of 3. That's 3 squared. And because the 9 is squared, the 3 squared would be squared as well. And when you have one exponent raised to another, you multiply the exponents. So that'd be the same as 3 to the 4th. Now, you could check this on your calculator. Right, the original expression was 9 squared, which is 81. If you go 3 to the power 4, you should get the same value, and you do. So you can check to make sure that the expression you got at the end matches what you started with. Question C, a little more complicated, but we want to express both with a base of 3. 27 is 3 cubed, and that's raised to the power 1/3. The cube root of 81 squared. Well, 81 would be 3 to the 4th. And remember from your work in 20-1, if you have a radical expression, you can write it as a power with a rational exponent. So in this case here, because it's the cube root of 81 squared, that's the power 2/3. You might remember that the denominator of the rational exponent tells you what root it is. It's a cube root, so the denominator is 3. Where the numerator tells you what power it's all raised to, so it's raised to the power 2, and that's why we have the 2 on top. So we can simplify this. First, each of these factors has a base of 3 with one exponent raised to another. The law says when you have one exponent raised to another, you multiply the exponents, keep the base the same. So for the first one, it'll be 3 over 3, which is 1 as an exponent. And for the next one, 4 over 1 times 2 over 3 is 8 over 3. And now when you're multiplying powers with the same base, you add the exponents and keep the base the same. And because I had that 3 over 3 with a denominator of 3, I can easily add it to 8 over 3 by adding the top number, keeping the same denominator. Oh, I'm sorry, I don't know why I wrote 8, because I looked at an 8 there. Base is 3. 3 to the power 11 thirds. Now, again, you could check this on your calculator. Take the original expression, put it in your calculator. 27 to the power 1 over 3 times the cube root, the cube root of 81 squared. And it doesn't matter if the squared is all of it squared or just 81 squared. You might remember from, again, Math 20-1, that'll give you the same value. What that's saying, it doesn't matter if you take the cube root first and square second, or square first and take the cube root second. It doesn't matter. So that gives us that irrational number. Well, that should be the same answer that we get when we take our simplified expression, 3 to the power 11 over 3. We get exactly the same expression. So our simplified answer is equivalent to what we started with. Okay, so try those ones on your own. Write each one with a power as a power with a base of 2. So 4 would be 2 squared, and because the 4 is cubed, the 2 squared would be cubed as well. And then when you multiply the exponents, you'll get 2 to the 6. For question B, it's 1 over 8, and 8 can be written as 2 cubed, so it's 1 over 2 cubed, which really isn't written as a power with a base of 2. So to do that, you move it from the bottom to the top, which causes the exponent sign to change from positive to a negative. And then for the last one, 8, which is 2 cubed, has to be raised to the power 2 thirds, times 16, which is 2 to the 4th, and that's the square root of 16, which means the denominator is 2 raised to the power 3, so it's 2 to the 4th to the power 3 halves. So when you multiply the exponents here, 3 over 1 times 2 over 3, the 3's will cancel and you'll get power 2 times 2 to the 4 over 1 times 3 over 2 would be 12 over 2, which is 6. And now you're multiplying powers with the same base, so you add the exponents and the base stays the same. So to check that, if we have 8 to the power 2 over 3 times, and it doesn't matter again what order we do the next part in, whether it's square root first, cube second, or cube first, square root second. I'll just do this one the same way it's written. It's the square root of 16 all to the power 3. So when we do that, we get an answer of 256, which is what 2 to the power 8 equals. So again, it just shows that the answer we got at the end matches what we started with. We've written it as a power with a base of 2. So now let's apply this to solving exponential equations by changing the base, by expressing both sides with the same base. So in this case here, you could actually express both sides with a base of 4, because 4 cubed is 64. And so on that right side, when you have one exponent raised to another, you multiply the exponents, keep the base the same. And now, this is an equation. The left and right side are equal. If the bases are equal, then it means the other parts must be equal as well. The exponents have to be equal as well. So we can equate the exponents and then solve for x by subtracting x from both sides and then dividing by 2, we get x equals 1. And if we check that, when we let x equal 1, 1 plus 2 is 3, 4 cubed is 64. When x is 1, the right side is 64 to the 1, which is 64. So it checks. You should never get these wrong. You can always check them. Question B, in this case, you cannot write 8 with a base of 4. Sure, 4 times 2 is 8, but that's not a base of 4. In this case, you have to change both bases to a base of 2. 4 is 2 squared raised to the 2x. 8 is 2 cubed to the power 2x minus 3. This will be 2 to the 4x equals 2 to the 6x take away 9. Bases are equal, so the exponents are equal. This is why we change the bases so that they're the same. It's an equation. If one part is equal, the bases, then the other parts, the exponents, must be equal as well. So if I subtract the 4x from both sides, I'll get a 2x on the right. I'll add the 9 over to the other side and then divide by 2. X equals 9 halves, or 4.5. So we can check that. 2 to the power of 2 times 4.5 is 512 on the left. On the right side, you're going to have, I'm sorry, I did that wrong. I used a base of 2. It should be a base of 4. So let me fix that. 4 to the power 2x. A large number, 262,144. So we should get the same answer on the right side. 8 to the power 2 times 4.5 take away 3. Exactly the same number. So that just shows that our answer is correct. Okay. This one says solve, and then we can check our answers using graphing technology. So we can check our answer on the graphing calculator. So again, in this case, we can write both sides with a base of 2 because 4 is 2 squared. So that'll be 2 to the 2x plus 6. When you multiply out those exponents. Bases are equal, so now the exponents will be equal as well. I'll subtract the 2x from both sides and then divide by 2, and we get an answer of x equals 3. So where these two graphs intersect should be where x equals 3. We can check it on our graphing calculator by putting the two equations in there. 2 to the power 4x as equation 1, 4 to the power x plus 3 as equation 2. If I go zoom 6 to set my windows to their standard settings, can't see the point of intersection here, so maybe we'll try zoom fit instead. So zoom 0 is zoom fit. And I'm going to change my x. Let's see that again. Yeah, I'm going to change my x max to, let's say, 25. and a scale of 5. And if I find the point of intersection, second function trace, number 5 for intersect, enter, 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 you can see you get an answer of x equals 3. Just can't see it. I maybe should have let my y minimum be something a little bit smaller, like let's say -2. And my y max doesn't need to be near that big. I could let it, say, be 100. And a scale of 5. And maybe I should have let my y max be a little bit larger, because we can't see the point of intersection of x equals 3, but we already checked it, so we know it's correct. Question B, we have to write both sides with the same base. It has to be a base of 3. 9 is 3 squared to the 4x. 27 is 3 cubed to the x minus 1. So that gives us 3 to the 8x equaling 3 to the 3x minus 3. Bases are equal, so the exponents are equal as well. So subtract the 3x from both sides, and then divide both sides by 5. Whoops, that's a -3. So -3/5 is the answer that we get. So again, checking that on the calculator. 9 to the power 4x is the first equation. 27 to the power x minus 1. Is our second equation. If I go zoom 0 for zoom fit, don't really get a good look at the graph, but let's see if we can get our point of intersection. It gives it at -0.6, which is what -3/5 is. So it checks. Okay. So from what we know right now, because we haven't learned about logarithms yet, some of our exponential equations have to be solved graphically. Again, in chapter 8, we'll learn how to use logarithms to do it. But for now, if we're going to solve these, we have to do it graphically. And so we're going to have to round our answers, because the answers will likely be irrational. 2 to the power 2x has to equal 3 to the power x minus 1. And if I find my point of intersection, -3.819, if I round to 3 decimal places, -3.819. And on a diploma exam, if there's a question like this, they would tell you how to round it. Then for question 2, 4 to the power 2x minus 1. So there's that one. The second one is 6 to the power x plus 2, and then a minus 1 at the end. Second function trace, number 5 for intersect. Approximately 1.999 or approximately 2. Negative. Okay? So Christina plans to buy a car. She saved $5,000. The car she wants costs $5,900. How long will Christina have to invest her money in a term deposit that pays 6.12% per year compounded quarterly before she has enough to buy the car? So the formula that we are given on the formula sheet, again, we saw this yesterday, is y equals a times b to the power t over p, where t is the time, p is the growth period, and b we saw was the growth rate. And so in this case here, she gets 6.12% per year, but it's compounded quarterly. So to find b, we have to take the 6.12% and divide it by 4, because it's compounded quarterly, which is 4 times a year. So that's the first thing we need to do. 6.12 divided by 4 is 1.53%. And so as a decimal, divide by 100, you'll get 0.0153. Now in this case here, her money is going to grow, so she has what she started with plus 0.0153 more every quarter. She has what she started with, which is 100% of what she started with. And so 100% as a decimal is 1, so it's going to be 1. I'll put a plus 1 on the end, so it's 1.0153. That's what our growth rate will be, because she has 100% of what she started with. That's what the 1 represents, plus 0.0153 more. So that's the b value that we will have to use in this case. Now, yesterday when we looked at writing equations from a graph, we saw that in almost all the cases, the a value was the initial amount. The only time it wouldn't be the initial amount is if the graph has been shifted up or down. Okay? That would be the only time that the a value would not be the initial amount. So in this case here, your initial amount is $5,000. That is what the value of a will be. And t is the time in years, and that will be divided, actually, it will be the time in months, because that's going to be divided by 4, because that's how many times a year the interest is calculated. It's calculated quarterly. And so if you write t in years, then p would have to be 1 quarter. Or if you write t in months, then p would actually be 3. Because if it's compounded quarterly, that's 4 times a year. That's every 3 months. Okay? So those two values, t and p, have to be in the same unit. So if p equals 3 months, then t will equal the number of months. And again, the 3 months comes from the fact that it is compounded quarterly, which is every, or I should say, 4 times a year. And 1 year, which is 12 months, divided by 4 times a year is 3. So P is every 3 months. So We want to know how long it'll take for this investment to reach 5,900. So we're going to have two equations here. Y1 will be 5,900. Y2 will be 5,000 times 1.0153 to the power t over 3. And we want to solve for t. So again, once we learn about logarithms, we'll be able to do this algebraically. But that'll come in chapter 8. So we've got one equation, y equals 5,900. The other equation will be 5,000 times 1.0153 to the power x over 3. We cannot solve this algebraically because we cannot make the bases the same. So we have no choice but to do it graphically right now. So zoom 0 for zoom fit. We don't see the point of intersection. If we try and find it right now, second function trace, number 5 for intersect, enter, enter, enter. It won't give it to us because we can't see the point of intersection. So when we look at our graph, we know that it's over to the right somewhere. We can just see at the very top, that's the line 5,900. And we can see the curve going upwards and to the right here. We need to make our x max larger. Let's make it 30 and a scale of 5. And see if we can see the point of intersection now. Almost, not quite. So we'll do one more. Let's change that to a 40. Now we can see the point of intersection. Second function trace, number 5 for intersect, enter, enter, enter. And it's 32.701 months. And then to find out how many years that is, we can take x and divide it by 12, because there's 12 months in a year. So approximately 2.73 years, or 2.725 years. That's how long it would take. Okay. And in this case, you'd actually have to round that up because the interest isn't calculated after 2.725 years. It's compounded every quarter. It's calculated every quarter. So you'd have to round this up to 2.75 is when it would actually happen. And then she'd have a little more money than she needs, but she'd have at least the 5,900. Determine how long $1,000 needs to be invested into an account that earns 8.3% compounded semi-annually before it increases in value to $1,490. So in this case here, the growth rate B will be 1 plus, because it's 100% what you had, plus, in this case, 8.3% more, but that's compounded semi-annually. So we have to take the 8.3% and divide it by 2, because semi-annual means twice a year. So 8.3 divided by 2 is 4.15. We'll divide that by 100 to write it as a decimal, and then add 1. So it'll be 1.40415. That's what our B value is, 1.0415. Okay. Now, our P value. In this case here, it's compounded semi-annually, which means twice a year or every 6 months. Hello, yes, thank you. Okay, so when we find out our T answer, it's going to be the number of months that it'll take for this investment to become $1,490. Our first graph, Y1, will be the 1,490. Our second graph will be for the equation. Principal times 1 plus I to the power T over 6. So remember, A represents the initial amount, which is 1,000. B is the growth rate, which we found is 4.15% per semi-annual. Write it as a decimal, and then you have to add 1 to it because the amount that you have is 100% every semi-annual period. You'll have 100% of what you started with, which is what the 1 represents, plus 0.0415 more. So back to the calculator. Y equals 1,490 is my first equation. My second equation is 1,000 times 1.0415 to the power x over 6. Zoom 0 for zoom fit. Again, we can't quite see the point of intersection, so we need to make our x max larger. Thank you again. Let's make our x max 60 in this case. Now we can see the point of intersection. Second function trace, number 5 for intersect. Enter, enter, enter. So it's at approximately 58.8426. 426, yep. So that is months. That would have to be divided by 12 in order to convert it into years. So if I take the x value and divide it by 12, so 4.9, which would have to round to 5 years. Because the interest is calculated every 6 months. So at 5 years, there'll be a little more than $1,490 in there, but if you back it up to 4.5 years, there would not be at least that amount in there. Okay. So, again, next chapter we'll learn how to solve these types of equations algebraically. We should work on page 364, questions 2 through 5 and 7. And we have our quiz scheduled for tomorrow for this chapter. Okay? So page 364, 2 through 5 and 7. Yeah.